Okay, welcome everyone to the 93rd meeting of New Directions in Group Theory and Triangulated Categories. Today our speaker is Eloísa Grifo from University of Nebraska, Lincoln, and the title of her talk is Searching for Modules That Are Not Virtually Small.
Great. Well, thank you so much, everybody, for coming, and thank you to Radib for inviting me to speak. I'm very happy to tell you a little bit about some joint work with Ben Briggs and Josh Pollitz. And this is a triangulated category seminar. So today's triangulated category will be the derived category, the bounded derived category of finitely generated modules over a ring, which I'll shorten to DBR. And for me, I'm a commutative algebraist, so all rings are commutative in Noetherian. And in fact, today, I'm going to be talking about local rings. Okay. So in fact, let me settle on some technical notation for the talk. So I won't need this right away, but I'll need it soon. I want to take my Noetherian local ring, and I'm going to want to take a minimal coin presentation for it. So if there will be a bunch of hats throughout the talk. If you don't like the hats, you can pretend that my ring is also complete, and then just ignore the hats everywhere. But so the completion of R, I can write as a quotient of a regular local ring, and I'm going to do this minimally. So I'm going to make the ideal that I'm quotienting by. I'm going to make sure it's contained in M squared. And later in the talk, I will remind you of what this number is in it when I need it. But I'm going to need to know what is the number of generators of I. So the sort of the number of equations that I need to define my ring R. And our story begins with one of my favorite theorems by Auslander Buchsbaum Serre, which is a characterization of regular rings, the simplest type of singularities, well, ones that are not singular, via homological methods. And the sort of original version that we would write maybe in a homological algebra class would say the ring is regular if and only if every finitely generated module has finite projective dimension. So maybe let me say that my module is called M, and I'm going to denote by Pdim the projective dimension over R, and I'm going to want the projective dimension to be finite. And in fact, there is a test module for this, right? I just have to look. So I've chosen K to be the residue fields. And so the projective dimension of K is finite exactly when the ring is regular. So this will be important later. There's this one module that serves as a test module for the regularity property. Now, in modern language, I could write a second version of this theorem using derived categories. So my ring is regular if and only if, in my bounded derived category, every object is perfect. And sometimes I'll refer to perfect as small. So a small object is a perfect object. Now, and I guess I could also write, K is perfect if and only if R is regular. So what I want to do today is I want to talk about writing an analogous version of this theorem for a different class of singularities. So I want to weaken the regularity assumption a little bit. I'm actually going to look at sort of the next class of singularities that one would study. And I'm going to tell you a theorem of Josh Pollitz that sort of gives a characterization and sort of V2 gives a characterization of a different type of singularities in terms of the triangulated structure of the derived category. So for that, I also need to weaken this side. I'm no longer going to be asking that every object be perfect. And to tell you the condition that we want to study, maybe first I'm going to just rethink about what being perfect means for a second. Well, it means that every object is in the thick closure of my ring R. So the sort of next best class of objects, well, depending on how you think about it, but for today's purpose, is a class that was first defined by Dwyer, Greenlease, and Iyengar back in 2006. And well, it's a class of objects that are close to being small, close to being perfect. So they're called virtually small. Well, the trivial object is virtually small. And if you take a non-trivial object, being virtually small means that you're finitely many steps away from being small. So it means that there exists some non-trivial object. There exists some non-trivial small perfect object that is built by, finitely built by M. So I'll think of this as sort of being finitely many steps away from having finite projective dimension. And throughout my talk, I'll write VS a lot. So VS of R will stand for this full subcategory of DBR of virtually small objects. So in fact, sometimes I might write like an object is VS, and I mean virtually small. Okay. And we'll need some things about virtually small objects later. So back in the paper where Dwyer, Greenlease, and Iyengar defined these things, well, they proved a lot of nice things, and particularly they give us some properties of virtually small objects. And so a lemma you'll find in their paper, that's really a consequence of a theorem of Hopkins and Niemann, is that if you take some non-trivial virtually small object, that's the same thing as asking. So the definition is that you build something that is perfect. But it turns out that if you build something that is perfect, finitely built, then you build the Kazoo complex. So KR, and I apologize in advance, sometimes I tend to write my K's a little small, but now I mean a big K. This is the Kazoo complex on a minimal generating set for the maximal ideal. And I gave a name to the maximal ideal of my of the regular ring upstairs. So maybe here, let me write MR. Okay, this is the maximal ideal of R. Okay, I'm going to need this fact in a little bit. I'll remind you of it when we need it. But so this is what's going to go on the other side of the theorem. And I'm going to replace regularity with sort of the next best class of singularities, which are complete intersections. And so throughout my talk, I'm going to be writing CI for complete intersections. Oops. And in fact, I'm going to refer to ideals as being complete intersections as well as rings. So when I say an ideal is complete intersection, I mean that the ring, when you quotient by the ideal, that I get a complete intersection. So being a complete intersection means that the defining ideal I is generated by a regular sequence. So in other words, this is a condition that the dimension of R, which remember is Q mod I, right? R is Q mod I. It means that the dimension of R is the dimension that we sort of naively expected. So I started from Q and I quotiented by n equations. So the expectation is that the dimension dropped by n, and being a complete section is when exactly that happens. So in other words, when I has the same height as the minimal number of generators. So for example, if I take my Q to be a power series ring in 2 variables, actually, let me call this Q. So I take Q mod x squared y squared. This is a regular sequence. This is an example of a CI ring. But if I instead take x squared xy, this is not CI. And this is kind of the first example of not a complete intersection that one would ever write. And it will appear again later in the talk. Okay, so the theorem that I've been promising is a result of Josh Pollitz, published in 2019. And what he proved is that our ring is a complete intersection. So this class of singularities we just defined, if and only if every object in our derived category is virtually small. So I no longer have a regular ring. I have sort of the next best thing. And so my objects don't have to all be small, but they have to be finitely many steps away from small objects. Maybe I should say that the implication that the RCI implies that every object is virtually small was already in Dwyer, Greenleaf, and Iyinger's paper from 2006, the same where they first defined the condition. And in their paper, they phrased the backwards implication as a question. And so this paper of Pollitz is really answering that question of Dwyer, Greenleaf, and Iyengar. So for today, my motivating question is, I think of this theorem as sort of the version 2, right? Comparing to the story for regular rings, right? This is the triangulated version of the theorem. And Auslander Buchsbaum Serre was born in the world of modules, right? But before anybody knew about the derived category. And so in this case, this is a theorem that was born in the sort of modern world of the derived category. And what I would like to do is that we would like to bring this back to the world of modules. So notice that the theorem says that if R is not CI, the theorem tells me that there exists some object that is not virtually small. And in fact, I will tell you later that Pollitz actually constructs a collection of objects that one of those objects has to necessarily not be virtually small. So he sort of knows where to look. But those objects are complexes. They really are not modules. And so we would like to ask, if R is not CI, does there exist a finitely generated R module that is not virtually small?
I have a question. So
yeah.
Regarding what you said just now about Josh's proof of this direction, so the complexes that he constructs, I mean, is there like an intrinsic characterization of them in terms of R?
I'm gonna write them down in a minute. Okay. They're sort of not his complexes. They're complexes that come from modular representation theory from the work of Carlson. So maybe some people in the audience will recognize them, but I want to write them a little later in the talk. So hang tight. I'll get there. Good question though. Okay. So and I'm gonna tell you right away that these complexes we don't have a trick in the setting that we're in to sort of extract modules that do the same, that have the same properties that we're going to need. So we can't just take Josh's proof and sort of, adapt it to get modules. So we're going to have to come up with some new, we're going to have to do something new. But before I tell you about how to attack the problem, maybe we should discuss, the first things that would come to mind. So some notes. Ultimately, in the regular setting, I have this test module. I would love to have one finally generated module that I could test being a complete intersection on. And there are some obvious things to try, right? Well, first of all, since K was a good module for the regular property, one could think about whether K is a good module to test complete intersections. But K builds the Kazoo complex. And always. So K is always virtually small. So the residue fields is not going to be a good test module for the complete intersection property. And yeah, so we got to go look for something else. But maybe the problem is the K is really good test module for regularity. We should be looking in other places in commutative algebra, algebraic geometry, and trying to find other modules that in other settings are good, give good characterizations of the complete intersection property. And so sort of the next obvious thing to try is something called the conormal module. And so remember, I is the defining ideal of R. So I lives over Q, not over R. But if I take I mod I square, this is now a Q module that's killed by I. So it's an R module. So this is now an R module that does, in other settings, control the complete intersection property. There are different theorems I could cite of that kind. I think the most recent, but also maybe more complete one is a result of Ben Briggs, who very recently solved a 40-year-old conjecture of Vasconcelos that said that R is Ci if and only if this conormal module has finite projective dimension. So if and only if this is perfect. So this is a characterization of complete intersections in terms of one module. And this, this is, in particular, I guess a silly weakening of this would be that if you're Ci, then M mod I squared is virtually small. Well, but everybody is. But one could hope that when R is not Ci, maybe this conormal module fails to be virtually small. And unfortunately, there are many reasons why this conormal module might fail to be virtually small. So if R has what is called an embedded deformation, in particular, then this conormal module is going to be virtually small. So having an embedded deformation means the following. So you look at so my R is a quotient of this regular ring. So you look in your quotient map and you ask, does it factor along the way to some smaller quotient of Q, such that when I write R as a quotient of S, this is a complete intersection map. So what I mean is that when I write R as a quotient of S, I'm quotienting by a regular sequence. Right, so the last map is a Ci map. Oh, and I should say, I want to do this in a non-silly way. So for example, if I now take a power series ring in 3 variables, I could take, remember x squared xy was not a regular sequence, and then I could throw in the element z squared. And the point is that z squared is still regular modulo x squared xy. So this would be an example where Q mod I has an embedded deformation, and this is an embedded deformation of it. And so the problem is, if R is an embedded deformation, it's not hard to prove that when R has an embedded deformation, then the conormal module has a free segment. And so in fact, that free segment is given by, you take your elements that give you the regular sequence on J, and those kind of generate a free segment. And so in particular, right, free segment's a small object, and so this is virtually small in this situation. Now, here's an excellent example of something that is not CI, but does have an embedded deformation. And so its conormal module is in fact virtually small. This is also not the place to look. And there's maybe a few more guesses one would try that do not work. And so we need to do something else. So maybe let me say right away that by the end of this talk, I will not have found a canonical test module for CIs. We do not know of a canonical test module for CIs. It might not exist. I mean, in this setting, right? Something that would fail to be virtually small when R is not CI. But what we will do instead is we will do something similar. Well, we'll do something different, but with the same spirit as Josh Pollitz's proof, or we'll construct a collection of modules to look at, of which some will fail to be virtually small when R is not CI. And so the main idea, as Josh Pollitz did in his paper, main tool we're going to use is something called cohomological support varieties. These were defined by Lucio Avramov in the 80s in commutative algebra, inspired by work of Quillen in the non-commutative setting. He defined them over CIs only, but you can find a general definition over any ring. For example, in work of Jorgensen, and more recently, Josh Pollitz, in this 2019 paper that I've been citing, he sort of started developing, that paper and subsequent papers started developing the theory more in the general setting, originally with the goal of trying to solve this problem. So let me tell you what is the cohomological support variety of an object in DBR. So hand me anything in DBR, and maybe let me say non-trivial. If it's trivial, it will just be the empty set. It will be its cohomological support variety. But that will not be very interesting for us. So we're going to write VR of M, and this will be a variety, which maybe will seem plausible in a minute. Not from my first definition, but maybe from the second. It will be something that lives inside of the space of minimal generators of I, right? So I'm going to look inside of I. I'm going to ask for its minimal generators. So really, when I quotient by MI, I get a K vector space. Since I declared, remember in the beginning, I declared the letter N to be the minimal number of generators of I. So this is the vector space K to the N, which I will also want to think about as a fine N space. But I really want to write it like this to also remember it has a vector space structure, because that will be helpful. And so inside of here, I could look over elements in I and think about their classes in this quotient. And the support will contain 0. So the things that are 0 are really correspond to the elements of I that are in MI, which means the ones that are not minimal generators. Or alternatively, I can look at M and I can ask, so remember Q is the regular ring upstairs, and I can now quotient, instead of quotienting all the way down by I, I'm going to quotient by this one element of I. I'm going to look at this hypersurface, and I'm going to ask, I need space. I'm going to ask if M is a small object or not over this hypersurface, whether or not it's perfect. And I will collect the F's for which M is not perfect. And so fact, and again, this will be more believable in a minute, this is a variety. What maybe is clear for now is that if I take some non-zero constant and I compare Q mod F and Q mod lambda F, well, that's the same quotient. And so if I take 2 points in the same line through the origin, they're either both in VR of M or they're both not. So what I've written to you is the affine cone of a projective variety. So I could have instead written this projectively, but I want to think about this definition through my talk again for emphasis, because I will exploit the fact that this is also a K-vector space. So let me give you an alternative definition. And it is not obvious that the two definitions I'm giving you are equivalent. That's a theorem that I hope you believe throughout the talk. So an alternative definition will be the following. I could think about the ring of cohomological operators. Some people call it the ring of Eisenbud operators. So there's as many as minimal generators of I. So it's a ring of cohomological operators over R. And take the Kazoo complex on that regular ring on a minimal generating set for I. And now I'm going to say lots of facts that are not obvious. So if I take the X of M against K over this Kazoo complex, and I'm collecting all the pieces, building this gigantic graded object, well, gigantic a priori. There is an action of this ring of cohomological operators on this X module. And so I could ask for the support over S. And in fact, this is all graded. So I'm going to put a little star up here to mean the graded support, the homogeneous graded support. And this is the variety that we want. So again, completely not obvious that this is equivalent to the definition from above. So in fact, I'm going to give you some examples, and I'm going to use the other definition to think through them. So the very first example that one can actually compute by hand, and I think is one of the most natural ones to ask about, is about the support of the residue field. What is it? So the question, remember the first definition, is whether my module, which is K in this case, whether there's perfect over these various hypersurfaces. So if you like, going back to modules now, I want to ask over this hypersurface, does K have finite or infinite projective dimension? Well, you might remember I put a condition in the beginning that the generators of I are all in M squared. None of them is linear. So this F is not linear. So for every single F you could choose, Q mod F is really a hypersurface. It is not regular. And so going back to the very beginning, Auslander Buchsbaum Serre says, this has infinite projective dimension for every single F. So I feel like this is not perfect for every single F. And so the support of K is everything. And I will refer to this as having full support. If I use the words full support at any point later in the talk, this is what I mean. Support is everything it could possibly be, as opposed to being the smallest possible, which is 0, whenever M is not trivial. I'm going to tell you about a second example. And in this second example, I will not calculate it by hand. In fact, it's very hard to calculate this example by hand. It can be done, but it would not fit in the length of this talk, even if I had started in the beginning to sort of construct, how one would do this. So it's not so easy to do this by hand. But by the way, it can be done with a computer. There are different algorithms for computing cohomological support varieties, but ultimately, this is something that can be done with finitely many steps. It's a computable thing. And in fact, there's a Macaulay 2 package called Thick Subcategories, written by me and Yanina Letts and Josh Pollitz. That in particular, it does various things it's called thick subcategories because it has something to do with thick subcategories. It computes things like levels, but it also computes cohomological support varieties. It is not exactly finished. The functions all work and compute things. It's just the documentation that's missing things, but you can find it on my GitHub. So anyway, one can compute these things. So you can compute the cohomological support variety of this. Well, this is the ring I want. And the theme through the rest of the talk will be that when you think about the ring as a module over itself, its cohomological support variety can be very interesting, and it contains interesting information. And so in particular, this is an example where the support is really, really fun. So I have 2 generators. There's 5 generators here. So this lives in 5-dimensional space. And there are 2. So maybe let me use chi 1 through 5 to mean like the variables of my 5 directions. So this variety is the union of 2 hyperplanes. It's the hyperplane where you set the first variable to 0 or the last variable to 0, where this is 1, 2, 3, 4, 5. So it corresponds to these 2 interesting generators. So maybe to emphasize that the support of R is important, what do support varieties have to do with our story about virtually small complexes? So remember, Josh Pollitz proved, here we go. It proved that being CI is equivalent to every object being virtually small. And how did he prove it? Well, he proved that those 2 conditions are equivalent to a third one. He proved that R is CI if and only if the support of R is the module over itself is the smallest possible. Remember, I'm writing the affine cone of my variety now. So the support of R contains information about the singularities of R. It at least tells me when it's CI or not. And so to tell you a little bit more about what he did and what are these complexes that I was mentioning before, let me tell you some facts from his paper. So if you take 2 objects in our bounded derived category, first, if M finally builds N, then the support of N is contained in the support of M. Moreover, the support of R is the same as the support of that special complex, the Kazul complex. Remember, it stands for the Kazul complex on a minimal generating set for the maximum ideal of R. So notice that if you put these together with the things I've said in the beginning, if you take a virtually small object, I said before, the Dwyer, Greenleast, and Iyengar proved that being virtually small is the same as building the Kuzul complex. But then this, maybe let me call this 1 and this 2. So this point 1 is going to say that the support of the Kuzul complex, it must be contained in the support of M. But the support of the Kuzul complex is the same as the support of the ring. So if you take a virtually small complex, necessarily its support contains a support for R. So the strategy is to find an M whose support cannot possibly contain the support of R. And then we will find our M that is not virtually small. So in Pollitz's paper, I mentioned before that he thinks about complexes that come from Carlson's work in module representation theory. So these might be familiar to some of you. So let's go back to thinking about that ring of cohomological operators. Let's say that I take a homogeneous element of degree D. There is a map induced by this F in the derived category from K to its to a shift, and the cone of this map, I'm going to call LF. And what Pollitz proved in this paper is that these complexes LF, the support of LF is a hyperplane. And it's the hyperplane determined by F. It's the hyperplane where, I'm writing F bar for sort of the thing that corresponds to F, right, in I mod MI. And it's the hyperplane determined by this F. So the problem is, so what did Pollitz do? Well, he looks at these complexes. If they were all virtually small, they would all have to contain the support of R, but they are hyperplanes in every single direction you could possibly want. Sorry, hypersurfaces really. And so ultimately, their intersection is 0. And so the support of R has to be 0 to be contained in all of them. So if the support of R is not 0, so if R is not CI, right, thanks to this theorem, then necessarily one of these fails to be virtually small. Now the problem is these are complexes, and in our setting, we don't have a trick. Now, as opposed to what happens in representation theory, we don't have a trick for converting these into modules. The problem being that the support theory does not respect taking syzygies, this cohomological support theory. So we'll have to do something a little different. And now I'm getting to the new results. So in this project with Ben Briggs and Josh Pollitz. So I'm going to tell you about a paper. Oh, goodness. So I'm going to tell you about results from a few different papers. This is from our first paper on this subject that got published in 2022. We attacked this problem by trying to find modules whose supports we could compute. Our real goal was to find modules whose supports are hyperplanes. And our dream was to find, for any hyperplane or any hypersurface, we would dream to find a module whose support is that hypersurface. We can't quite do them all, but we have a trick for getting linear spaces. So we show the following. Suppose that you found a J that now is bigger than I. This is some ideal in Q in the regular ring that contains the defining ideal of R. And I'm going to ask the JBCI, so J itself is generated by a regular sequence. Now you can think about the R module that I'll call M. That is Q mod J. So this is, I can both think about this as a ring, right? A quotient of my original cube, but I can also think about it as a module over R. And in fact, I want to do both. But for now, I'll think about this module. And what we showed is that to compute the support of this module, you think about the inclusion map of I into J, and note that that inclusion map sends non-minimal generators to non-minimal generators. And so this induces now a map of K vector spaces. And you look at that map of K vector spaces and compute its kernel, which is a linear space. Our dream is to find such guys where this is not everything, right? Because we don't want to contain the support of R, so we want this to be small in some way. So at least to be a hyperplane, that would be wonderful. So I want this kernel to not be everything. So I want to have something that doesn't go to 0, which means I want to have some element in I that is non-zero here, so some minimal generator of I, that when I look inside of J, I want something that is still a minimal generator of J. So I want I want to find such a J that shares minimal generators with I. So I kind of want to do two things at once, right? I want to pick some minimal generator of I, and I want to sort of complete it to a regular sequence. But at the same time, I want to make sure that that regular sequence contains the original ideal. And that's where things get a little hairy, to make sure that you can do such a thing in different directions. So in our paper, the same paper from 2022, we showed that if you take a minimal generator, so I really mean you're in I, not in MI. So this is a minimal generator of I. If you take a minimal generator that also has minimal amatic order, so if you want to think about, instead of the local setting, think about the graded setting, I'm sort of talking about the degree. I want something of minimal degree. So I want something of minimal amatic order. Oh, maybe let me say let. There's always such a guy of minimal amatic order. And for the ones of minimal amatic order, there exists a CI ideal J that contains I and that has F as a minimal generator. Right? So not being an MJ means it is a minimal generator as well. So something that is not in the kernel. And so in particular, this means that for these guys of minimal amatic order, we can build things that give me hyperplanes. So as a consequence, so the theorem I'm writing is in some sense a corollary of the two lemmas I just wrote. So as a corollary, we can solve the problem in some situations. The difficulty is I can only control things, make sure that this will not be full if I'm starting with a minimal generator of minimal order. So one way to get around that, or to embrace it maybe, is if every minimal generator of I has the same amatic order, if they all have minimal order. So I'll call those equipresented. So it's like saying, if I was in the graded setting, I'm asking that every generator has the same degree. And then, given all this, we show that RCI, if and only if every finitely generated R module M is also virtually small. And in fact, we did a little more. When K is infinite, in this previous thing, so if K is infinite, I can choose this J such that now when I think about the ring Q-J, this is an Artinian ring. And that part is easy. It's sort of saying that the regular sequence that generates J is maximal in R. But then when I rewrite that ring appropriately, that it's an Artinian hypersurface. So it's really that you start from F and the remaining elements you pick are linear, which means that when you quotient by the remaining things, that you still remain regular. In fact, that you sort of get rid of those guys. And at the end of the day, your ring Q mod J can be rewritten as regular ring mod one thing, which is really F. So when K is infinite, you could ask if every Artinian hypersurface that you can write as a quotient of R is virtually small. I think about the original Auslander Buchsbaum Serre. So I stated it in the local setting, but you can even think about the global statement. Auslander Buchsbaum Serre says, I am regular if and only if every quotient to a field is small, is perfect, has finite projective dimension. This is an analogous statement to that. It's saying I am Ci if and only if every quotient, now not to a field but to an Artinian hypersurface, which is kind of the next best thing, is the next best thing to small. It's virtually small. And this is only here for a technical reason, for us to be able to choose this appropriately. It doesn't mean they can't do it without the infinite field case. All right, so maybe just to emphasize the proof, the point is if you take any element in I, any minimal generator, I can construct this special module. So these are not the LFs from before, I'll call them MFs, but they're sort of playing a similar role. But now, instead of giving me the hypersurface determined by F, what I will get is some support that doesn't have the thing corresponding to F. I'm now avoiding this one point. And this is a hyperplane, in fact. And if all the MS were virtually small, then in particular, the support of R would be contained on the support of every MF. So it'd be contained in an intersection. But for each F that fails one of these guys, so there, for each non-trivial F, let me say this, non-trivial, fail every single point, so this has to be 0. So the support is 0, and then Josh Pollitz proved that implies that R is CI. So again, what did I need represented? I needed represented to guarantee that I can build these MFs in every single direction. However, I can always construct at least one of these MFs for sure, because I always have elements of minimal lemmatic order. So note, so you can, you can always construct at least one. Maybe let me emphasize at least one module whose support is a hyperplane. Okay, so when K is not infinite, maybe I can always say I can always construct something support is contained in a hyperplane. It's a linear space contained in some hyperplane. So in particular, if I happen to know that the support of R was everything, the support was full, it can't be contained in a hyperplane. And there's at least some module. I should emphasize, this is a module, not a complex. There's at least one module that is that gives me a hyperplane. So this M cannot possibly be virtually small. But in fact, I don't actually need here that the support of R is everything. I just need the support of R to not be contained in a hyperplane. So how do I say that the support of R is not contained in a hyperplane? Well, it means now is when I think about this K to the N as a vector space again, it means that the K span, and think about VR of R as a subset of K to the N, if it spans everything, then it's not contained in a hyperplane. And so then you can always solve the problem in such a circumstance. So this led us to think about what is VR of R and what information does it contain. And there's lots more about it I'd like to say, but for the purpose of today, I'm just going to tell you that in a more recent paper, one that just got published maybe a couple months ago, so with Ben Briggs and Josh Pollitz, we show that if you take a Golod ring that is not CI, so Golod rings that are CI are hypersurfaces. So I'm really saying if you take a Golod ring that's not a hypersurface, then the support is full. And I won't define Golod rings, but I'll just say they're sort of an extremal class of rings. They have extremal Betty numbers. K has extremal Betty numbers. So maybe let me just say out loud, maybe I won't write. So corollary, when R is Golod, but we can solve this problem. We can find a module that is not virtually small. Was there a question?
No.
Oh, okay. I could hear it. I think somebody might have turned on their mic.
Yeah,
okay.
It was me. Yeah.
Okay, so in my last couple minutes, let me say two things. One is I'll mention one more class where we can solve the problem. So, the reason we needed equipresented over there was to make sure that we really can construct all these, different hyperplanes in different directions. But you don't necessarily need to build all the hyperplanes in all the directions to solve the question, right? If you knew something about the support of R, you'd be in business. Or if you were able to somehow build some modules, a few of them, whose supports intersect 0, you'd also be in business. And so one circumstance where you can do this, and now I'm going to veer away from local rings for a second and think about graded things instead. So if you take a Stanley-Reisner ring, a quotient of a polynomial ring by a square free monomial ideal, then R is CI, and now there's no assumption on the fields. In this case, we can construct these things with no assumptions on the field. It is still true that every Artinian hypersurface is virtually small over R. And so again, that, every module is virtually small if and only if R is CI. So let me finish in my maybe last 3 minutes. Let me finish with an example. Maybe just to give you a feeling for how this works. And to show you that at the end of the day, we've now reduced the problem in part to linear algebra and a little bit of elementary commutative algebra. So this is not CI. This was my first example of a ring that is not CI. And what we want to construct a module that is not virtually small is we want to look at this ideal. This is my I, right? And I want to complete it to a regular sequence that contains this ideal in some way that shares minimal generators. So I'll fix x squared. And if I do x squared y, that's a regular sequence and that contains I. I could instead try to keep, the other minimal generator that I've chosen here. I could have kept x, y, and try to complete this to a regular sequence. You could do x plus y, and you can check this does contain I. So I'll even write you the supports, but a priori, right away from what I've said, one of these is not virtually small. So I'm in two-dimensional space, and these are both going to be lines, they're supports. They're lines that one avoids 1, 0, and one avoids 0, 1, right? If this corresponds to 1, 0, this corresponds to 0, 1. And in fact, since I still have a few minutes, let me just compute the support of M1 to emphasize what to do. So what I want to do, I'm going to go from 2 generators to 2 generators. So I'm going to write a 2x2 matrix. And what I want to do is I've taken the old generators and I want to compare them to the new ones, right? So I've taken x squared, and in terms of the new ones, that's 1, 0. And now I've taken xy, which I write by multiplying y by x. But I'm really, I've passed on to k. I'm doing this in the field. I'm killing off things in the maximal ideal. So this is really a 0. Okay. So this is the map that sends the first coordinate to itself, and the second one to 0. So the kernel. I wrote just the matrix. I meant to write. I want the kernel of this map, and that is when the first coordinate is 0, which does not have, the thing corresponding to x squared, which is my first generator. You could do the other guy. I should say it is not chi2 equals 0. The other guy is actually chi. I'll write it out. The other guy is actually chi1 plus chi2 is 0. But what matters is it doesn't contain the second. It doesn't contain like chi2. And so the intersection of these two lines is 0. So one of these, but the support of R is not 0. In fact, the support of R is full in this case. Okay, now I'm done. Thank you very much.
Thank you, Eloísa. Can we all unmute ourselves and give the speaker a round of applause now? Okay, if you have any questions for the speaker, you can ask them now. Is it a reasonable question to ask whether one can look at, I don't know, complete intersection varieties and try to have a similar characterization of in terms of the boundary derived category?
I mean, we do, right? Like, so Josh's theorem says.
Oh, I see. Yeah, right. Okay, I see. Yeah. Right. Sorry.
Now, what you could ask is, what if you take other singularities?
Mm-hmm. Yeah.
Could you ask? Can you characterize Gornsteinness in terms of
sure.
And I mean, I would hope so. I think that would be a beautiful theorem. We do not know. I think one potential snag is that there are multiple theorems in commutative algebra that say, your regular if and only if this, your complete intersection if and only if this, and then past complete intersections is all wild, and then insane things happen, right? Like talking about cyclic closures or minimal models and deviations, things like this.
Mm-hmm.
So there is a potential for this to be such a situation, right? Where there's regular rings, there's complete intersections, and everything's wild. But I'm hopeful that there might be some way of characterizing other singularities, like Gornstein or Cohn-Macaulay,
right,
in terms of the structure of the derived category. But we do not yet have such theorems. I mean, to be fair, Josh's theorem is not so old, right? And so I think maybe if there is a hope for such a theorem, maybe what we need is to develop the tools a little better, right? Like these support varieties, they've been around for 40 years, but for the first 30 plus, people were mostly working, the ambient rings were complete intersections. And to be able to do these characterizations, you kind of need a general theory that's, only now being sort of systematically developed. So if there is hope for such a theorem, please.
There were some people who were trying to characterize Gorensteinness in a different way via these things called complete hereditary cotorsion pairs. But when you translate that into the language of what one might expect here, you don't get you get nothing new.
Oh,
I think.
I see.
I mean, I think I showed this to Josh a couple of years ago. Like when you translate it to the language of rings and what happens here, you get absolutely nothing new. But there is but in that kind of abstract generality, probably it is something interesting. It's a paper by Sergio Estrada, Peter Thompson, and Lars Christian Winterson, and 3 or 2 people from China.
Okay.
And they do lots of
I don't
abstract
know this
things.
paper.
But towards the very end,
yeah. That sounds very nice. Yeah, I mean, I would love to have such a theorem. I would love for anyone to prove such a theorem, because I think it would be beautiful to have such a characterization. But
if I find I think I'm right. I think I was right with the names. I can see if I can find the paper, and I can just send you an email with the theorem number.
Sounds great. Thank you.
Any other questions? Anyone? Let's see. Oh yeah, yes. I think somebody asked me this by mistake in the chat via a DM. Will the slides be? I mean, will the notes be available afterwards?
Oh, I can make them available. Yeah, I can make a PDF and send it to you. Yeah. I'll make a PDF of my pretty notes from before the talk instead of the ones that I wrote during the talk. I use some prettier ones that I wrote to myself before. So I'll just share it with you, and you can.
Is this a subset of that?
Yeah, for sure. Yeah, I usually write more notes to myself, that I don't write down. So yeah.
Thank you. Yeah, I really like this example at the very, very end with this VRM1 and VRM2 computations. They're very neat.
But you could do this, now you can see it's really easy, right? That's kind of what I like about this is in the end, you reduce this to completely simple linear algebra, right? What the trick is finding these complete intersections. Right? So what we haven't proved is that if you hand me anything, any I, that I can write complete intersections, that sort of, go in all the different directions that you want. That's the problem, right? If you can write n different things that each avoid, a different direction, their intersection is going to be 0 and you'll be good. But the problem is proving that you can do them in all directions, right? This business about M-adic order is the only situation where I can guarantee that in every direction I can build it. But on the other hand, I've never seen a ring where the strategy doesn't work. Like if you had me any ring, it doesn't have to be represented, but it's something explicit. I just have to go find these regular sequences. And in fact, sometimes you find regular sequences that share multiple minimal generators with I, which is going to drop the code dimension even more. And, you could sometimes do this quickly, right? You don't need to find n things, you find 2 or 3 or whatever. The problem is proving in general that for any ring this can be done is what we cannot do yet.
Yeah, in practice, as you were saying, like in most cases, your I will have a decent enough, or will have some presentation that will be workable.
Yeah. If you hand me the presentation, then I can do something, right? Something explicit. So I've never seen an example where I can't do it. In fact, our paper has examples of things that are not represented, explicit things where you can just do it by hand. I like that you can do it by hand, right? In fact, you can, we have some code that will go find these.
Yeah, I was gonna say, like this thing that you and Janina wrote. I mean, one can also use that and compute these things much more easily, right? You made a comment when you're talking about that package. You said something about, I mean, it's not incomplete. Like, what were you saying? Like, you said some more work.
So we would like the package to come with Macaulay 2 in the future. But for that, all the documentation needs to be clean and pretty. Everything is so the package is complete in the sense that you can use it. You can download it to your computer. You can run it in Macaulay 2. All the functions work and give correct answers.
Yes.
But what is missing is documentation for some of the functions. Like we need to write more examples, more tests. There's a difference between writing a package that works. Yeah.
But
There's a difference between writing a package that works and one that is good for, mass consumption. And so it's not, it is, if any of you wants to use it, it's just get it from my GitHub, but use at your own risk, because it's not finished in the sense that, we're always doing we're still making small changes here and there. We improve it. Like Yanina just did a overhaul of some of the level functions in the last month that made it nicer, more efficient. And the current code for computing support varieties, it works, it is nice, but it will be better in a month or two. I'm working on something that will make it much more efficient and much faster. And so it does work. You can use it, and it will be even better in a few months. Right. And soon, I hope, will come with Macaulay 2.
Right. Okay. Any questions or comments? Anyone? Okay. In that case, let's thank Eloísa again. Okay, thank you all for coming. We are scheduled to have, I think, Paul Stellari next week. And thanks for